Hi, everybody. We're going to go ahead and get started because we have a jam-packed agenda. Thanks, everybody, for joining. This is Mike Lipnick from the University of California, San Francisco, and the Open Oximetry team. This is our first Open Oximetry Collaborative Community Meeting for 2025, and we're going to jump right into it. Just as a reminder, we are recording this meeting, and we would ask everybody to try and mute their microphones. But we will have discussion at the end, so feel free to raise hands and take yourself off mute at that point so we can have some discussion. The purpose of this particular meeting is going to be relatively focused. We're going to talk about some of the new changes in the FDA draft guidance on pulse oximeters that came out in January 2025, which I'm guessing most folks on this call have already familiarized themselves with, but we're going to dig a little bit deeper into some of the statistics that are proposed in that. And that's the main focus of this meeting. We're going to try and talk about some opportunities for data sharing and also exchanging ideas, and ultimately hope that several folks will be submitting public comments, which will be due March 10th to the FDA. So keep an eye on that. And for those of you who have not gone through the new draft guidance, this QR code can be used, and we'll drop a link in the chat. Here's the quick agenda for the next hour or so. We'll briefly go through some of the main changes in the statistical analysis plan and the new guidance, and then we'll have a series of brief presentations from different teams and individuals who are working on trying to understand the implications for some of the new statistical methods, considering alternative methods, strengths and weaknesses of what's being proposed compared to what there was previously. So we'll hear a little bit from these teams that are listed here, and then we'll open it up, and at the end we'll have some discussion. So briefly touching on some of the big changes that have been proposed in the new draft guidance. And again, the guidance is a draft, won't be finalized, TBD when that will happen, but open for public comment until March 10th. So some of the big changes are cohort size and diversity. The cohort size, this has been discussed in several of the prior collaborative community meetings. 10 was the recommended minimum, and prior controlled desaturation verification studies. The new recommendation is 150 participants, which gives you a total of 3,000 paired samples, SaO2, SpO2, and which is about 20 per participant. So that's a big change. In the new standard, or in the new draft guidance, there's a recommendation to have at least 25% of participants in each Monk skin tone scale grouping, 1 through 4, 5 through 7, 8 through 10, light, medium, dark. And that of the darkest Monk skin tone scale grouped individuals, at least 50% of those participants have an individual typology angle measured by a colorimeter of less than -50, darker than -50 as measured at the forehead. There's a recommendation that data pairs are distributed equally using the Monk scale across the desaturation deciles. And there is mention of the potential to use an adaptive study design, though there is some uncertainty around the minimum number of participants, which seems to be still 150. The success criteria for a device that would be considered to have an acceptable level of performance, overall accuracy is ARMS less than 3%. That's a change from previous where it was less than or equal to 3% for finger probes, and then less than or equal to 3.5% for ear clip probes or reflectance devices. Now all devices are less than 3%, and there's the new addition of a 95% confidence interval. So that's a relatively significant change for the ARMS. Disparate bias with Monk skin tone scale and disparate bias for ITA, those are both new. And so now there is a requirement to do an analysis of disparate bias across the MST groups with these different performance cutoffs. So less than 1.5% difference between groups in the higher saturation range, above 85%, and less than 3.5% difference between groups in the light to dark group in the 70 to 85%. And then for ITA, it's a modeled 100-point range in ITA at the probe site, but the same thresholds are to be used. All of these success criteria have a recommendation around confidence interval. So with that, we're going to jump into our presentations. John Feiner is going to be up first so that we can make sure that we have time. John, I'm going to stop sharing my screen so that you can start sharing your screen. So feel free to do that whenever you want. And we can make sure you got access. And again, please save comments and questions for the end. you can put comments anytime into the chat so we can keep track of them, but we will do like open discussion with all the presenters at the end. So questions into the chat, and John, over to you.
Are you seeing my screen?
Yes, we can see your screen.
Beautiful, beautiful. Okay, you know, I went through a lot of these calculations myself so I could get a feel for this, and this is one of the sample sets from OpenOx. I took the largest sample set, and I just wanted to point out that it's a solid sample set. Well-performing oximeter. This is 120 subjects. There was a reasonable skin balance, and it performed with an overall ARMS of 2.16, easily within an upper 95% confidence level, less than 3, and with a reasonable mean bias. So we're starting with a reasonable data set here. And what I wanted to do, again, you already mentioned the disparate bias, which is an attempt at measuring the effect of the skin on the oxygen saturation, or the SpO2, or the bias. And there are different limits between the ISO and FDA proposals. And the FDA requires the 95% confidence limits. I'm showing the different proposals below. They're similar, but significantly different. So I'm just going to try to give everyone a feel, including graphically, of these 3 different measurements with a sample data set. This is the ISO calculation. And ISO just basically has you take the individual mean bias and plot them against the individual typology angle at the site. So this is the dorsal finger, and you can see this linear regression with the 95% confidence limits. The bands, as you see, widen, and that is going to produce larger 95% confidence differences here. So you can see this plots out and shows the difference of the predicted point at -50 and +50, and that comes out to be a disparate bias of 2.95. I did put in the 95% confidence interval here, which is 3.71, which is still below the ISO requirements. So this is a pretty simple calculation to do by doing these individual data points and predicting. It took me longer to read it than to actually almost do it. Pretty simple concept of what disparate bias means. Now, if we do this with the FDA technique here, it's a little different, and the FDA does not really specify the model. I understand from people involved that it's a mixed effects, which basically means you're taking into account the subjects. It's a repeated measure calculation using all the data. And this does require the 95% confidence limit. And there's a lot of reasons that it turns out that these calculations ended up almost exactly the same. And that's partially because while there's no weighting required in the ISO standard, there was a pretty even number of data points for each subject. So it actually turned out that the calculation, while more complicated, I've been doing mixed effect modeling for a long time, so it was not that challenging. And in some ways might be easier if you do it regularly. Resulted in almost the exact same numbers in the same upper 95% confidence limit. I'm going to point out that this, with the 95% confidence limit, did not pass. It was not within the 3.5% that the FDA requires. But I just wanted to give people kind of a visual feel of how this calculation looks. And in some ways, it's really not that challenging. And I did pick on an oximeter that does. You can see there is an overall trend. It's important to note that because the confidence limits of a regression widen as you get further away, this means the confidence limits of a difference from the extremes is going to be fairly wide. And then I wanted to also show people what the otherwise, the pairwise comparison look like. And this is a pretty simple calculation showing the individual biases and then the differences with the confidence limit. The biggest difference here, not surprisingly, was from light to dark, and the upper 95% confidence limit was actually within the FDA standard. So this is using Monk scale. This was at the forehead. Again, not a challenging calculation, and seems to be an easier threshold to pass. The important things to recognize here is while these differences seem pretty minimal, the overall difference in the 95% confidence limits be, present a pretty big challenge with the FDA standard. So the confidence limits are going to be wide because they are from the two different extremes, but this is also not a tight fit. If you look at the variability of this regression, the R squared is not that high. And so that is going to produce a pretty big confidence limit. So the FDA standard is both narrower than the ISO standard, and requiring a 95% confidence limits might make it almost impossible to pass, because it effectively means the point estimates of the effect needs to be very, very, very small. I'm going to point out other people have done some lot of work on power analysis, but the narrowing of the confidence limits as you add subjects really gets very, very minuscule at the higher ends. I mean, most of the power of narrowing a confidence limit would happen in the first 20 to 30 subjects. So I hope this gives people kind of a feel for the calculations, because we're going to be seeing disparate bias talked about a lot. And that is all I have.
Thanks a lot, John. Appreciate that. No, that was great. And again, please keep the questions coming. We will circle back to those. Next up from the Hypoxia Lab team at San Francisco is going to be Danny Chen. Danny, while you're sharing your slides, for those who've joined in, thanks for joining. This call for OpenOx, it's a little bit more stats and technical focus. So if you've joined some of our other calls, you probably have found them to be slightly different. This one is digging deep into the stats of the new draft FDA guidance, and with the overall idea that there's a lot of new stuff in there, a lot of great ideas on how to ensure that pulse oximeters perform more equitably. But we're trying to figure out, are these actually going to raise the bar, or are these going to make add challenges and barriers to market entry that may actually have some of the opposite intended effect? Thanks again for joining. Danny, over to you.
Okay, so I'm going to present some of our work on sample size calculations using simulated data based on some of our tested devices. The general pipeline of our work is divided into four main components, which are data simulation, hypothesis testing, power calculation, and sample size estimation. Our calculation was based on the linear mixed effect model, which takes in the SpO2, SaO2, and ITA values as parameters. So we generated simulated data on these variables and performed hypothesis testing for 1,000 times to see whether the estimated difference in bias within a specified ITA range was significantly different from the acceptance threshold. And we estimated the sample size so that for 80% of the time, we can reject the null hypothesis. We'll be showing the sample size estimations from two of our devices. The first is one of our reference devices, which has a large sample data. And the second one is one of the top performing OpenOx devices in terms of ARMS. Here is the table showing the different sample sizes estimated under different scenarios for our reference device. The upper table shows sample size estimations in the lower set range, which is SaO2 less than 85%, and the lower table shows the sample size estimations in the upper set range, which is SaO2 greater than 85%. The columns highlighted in yellow represent the parameters that are changing in our sensitivity analysis. So the first highlighted column is the ITA range, ranging from 70 to 100. And the second highlighted column is the acceptance criteria, which are 3.5 for recommended by the FDA, and 4% are recommended by ISO. And the next column is delta bias, which quantifies how the SpO2 minus SaO2 bias changes as ITA varies within the specified range. And the last column highlighted in red shows the estimated sample size for each row of conditions. The red rectangles outlined here shows the requirement recommended by the FDA. So for SaO2 less than 85%, to achieve 80% power, and for ITA range of 100, 142 subjects are needed. And for SaO2 greater than 85%, 120 subjects are needed. So we have enough power to say the delta bias is significantly different from the acceptance criteria. When comparing the acceptance criteria column and the delta bias column, we notice that when delta bias gets closer to the acceptance criteria, the number of sessions or the number of subjects in the last column increases. We also calculated delta bias in simulation cohort sizes of 10, 20, 30, and so on. These two figures show their distributions. The left plot represents the lower set range, and the right represents the upper set range. We can see that after cohort size of 60, the distribution seems to become stable. And here is a similar table from the top performing device. For different ITA ranges, the delta biases stay consistently low, which are less than 0.1 for the lower set range and less than 0.05 for the upper set range. And we saw that since the delta bias is far away from the acceptance criteria, the sample size estimated to achieve the 80% power is also relatively small, which is 46 subjects. And for this device, we also did a simulation cohort size of various sizes. And it looks like the distribution of delta bias becomes stable after cohort size of 50. So from our analysis, we observed a close relationship between the estimated sample size and the distance between the acceptance criteria and the observed delta bias. So we wonder if there could be an adaptive design for a device with less than the proposed 150 subjects. That's all. Thank you.
Thanks a lot, Danny. Please keep the questions coming in the chat. And our next speaker is going to be Tyler from the Hypoxia Lab to round out the team here. Thanks a lot, Danny, for the talk. While Tyler's sharing screen, just a couple of quick things. As Danny mentioned, the ideal sample size, it depends on the performance of the device under test. We're seeing lots of devices where there's marginal or no benefit to testing in the larger sample sizes, and others where there is, and we're trying to come up with a method where we can, optimize to the test at hand. Hand over to Tyler at this point, and we'll circle back.
Thanks, Mike. So for this part of the talk, I wanted to give you a flavor of what this might mean for several different devices. So I'm presenting a data set of 34 devices tested in the pulse oximetry lab, the Hypoxia lab at UCSF. Some of this data was analyzed and presented at the ISO Joint Working Group and came out of those discussions. So what we're looking at here is all the different devices, SaO2 on the bottom and SpO2 on the y-axis, and the colors represent skin color. So dark is red and lighter skin colors are blue. And the first observation is that in most cases, oximeters tend to follow a line. It may not be the line of unity, but they follow their line. For example, we can look at device number 3. So device number 3 here, we can see that it exhibits a positive bias all along the saturation range, but is relatively internally consistent. The consequence of failing to fall along the line of unity is an increased ARMS, in which we see that as a 3.3 right there. Secondly, that we can see in some cases, there is a distinction according to skin color. So you might notice this in device 3 again, where the red skin colors, the darker skin colors are kind of shifted higher. Thirdly, we can see that in some devices struggle with low-end saturations. So, and this may be true whether both in darker and in lighter skin subjects. So we can see this here in device 1, which had a quite a low performing or high ARMS, but a low performing device, which falls off near the end of the saturation. We can see it in device 6, which was performing well and then struggled in the low ends, or for instance, in device 25, which had a similar thing. And you can see that just visually, there didn't seem to be a lot of distinction between skin tone in these for these troublesome areas. Right. So we'll move to, apologize, I'm navigating. So this is looking at, so this is what Dr. Feiner presented in terms of looking at disparate bias in the upper saturation ranges. So again, y-axis is the mean bias, SpO2 minus SaO2, and the x-axis is the ITA. So basically, we can see the bias by skin color. This is one way of looking at differential bias, as we talked about. And you can see for each of these devices here, it'll show us the delta bias between 50 and minus 50 and the number of subjects. So what we first note is striking is that a lot of plots, a lot of oximeters have a pretty flat line. So the delta bias is not high in a lot of cases in the higher sat ranges. So we can look at, say, device 25. So it's a great looking device when you look at the upper range of differential bias here with a mean bias of only 0.55%. But if you recall, it was a low performing device in terms of how well it did in ARMS. And what I should also point out is that these red rectangles are the occult hypoxia areas. So these are areas where it's SpO2 greater than 88 when the SaO2 is lower than that. So what else were we saying? So second, we can also look for device 1, which has a flat-ish regression line, but also was a poor performer, if you recall from the other graph. And the other thing we can note is that a lot of these slopes are down and to the right or up and to the left, as I kind of think about it, indicating that if there is a trend, there is a trend towards the positive bias in the darker skin color ranges. So we can look at, for instance, device 32. We can see that this device had a fairly high amount of ITA dependence, and it's particularly high in the lower saturation ranges, where a delta bias of 3.66. What's interesting is that this device 32, had an overall ARMS of 2.9 and would have passed by that criteria, but you can see that there are a number of outliers in the occult hypoxemia range. And then moving on quickly to look at percent modulation, because we know that this is something that affects things. So what we see here again is a bias on the y-axis and along the x-axis, percent modulation in the logarithmic scale. So 1% is approximately close to the middle here. So the point here is that bias is not totally related to percent modulation either. We can see in device 3 that device that had that shifted best fit line actually had a lot of subjects with a pretty high percent mod above that 1% mark. You can see here that the solid markers actually are the ones with occult hypoxemia in dark-skinned people. And this happened at pretty reasonable, what one usually would consider reasonable percent modulations. There's a suggestion of a slight slope here. As the percent mod gets smaller, the error gets higher. And of course, there are poor performing devices like device 13, which had a range of errors all throughout, and even including occult hypoxemia, all throughout the percent mod range. And I think that's going to, yeah, device 27, which exhibit a fairly reasonable amount of error throughout the range of modulation. All right, and then very quickly to wrap it up. So what we wanted to show here is that we can see that device 13, if we take device 13, when we talk about occult hypoxemia, this is a device that had occult hypoxemia and a pretty, not a good ARMS, ARMS that would have passed. But we see the occult hypoxemia is driven by one subject here, and their personal regression line was not on the what you would think of the regression line for the rest of the device. suggesting that what is playing into the hypoxemia, the occult hypoxemia here, may not be so related to the device or make question whether or not it's related to the device itself or something inherent to other factors. And this is the same in device 32, where you can see that this occult hypoxemia driven by this individual, which even though it had a pretty reasonable disparate bias at the upper sat range, it was that person was an outlier in the lower sat range, which is indicated by the arrow. So that's, in summary, that's really what the range of things we wanted to see in these devices, that skin color, percent mod may make a performance worse, but they don't fully characterize devices. And it's pretty, at least visually, easy to sort of see where a good performing device is and a good performing device isn't. And I just wanted to say that all this data is available on our PhysioNet repository. The new version is about to be published any minute now, which will include all these devices as well.
Thanks a lot, Tyler. And if anybody has any issues accessing the data repository, please go ahead and reach out to us directly or through the chat. You can also find links to that through the website. In the interest of time, I'm going to hand over to Gary Gray, who can introduce himself and get right into it. Thanks a lot.
Hey all, my name's Gary Gray. I'm the former FDA statistician, worked there for a long time.
I can't hear you quite yet. If you're
Can you not hear me? Hold on.
Okay, all good. Sorry.
Is it good now?
Yep, all good. Sorry about that.
Okay, sorry. Okay, so hi, my name's Gary Gray. I'm a former FDA statistician, long time there, and in the last 8 years or so, I've been in independent consulting doing statistical work. So I was, Mike asked me last week to give some sort of high-level stat comments on some of the things I see in the guidance. Okay, so we've seen this already. The FDA draft guidance has 3 different criteria for success, as they call them: accuracy, non-disparate bias for across MST groups, non-disparate bias for using ITA, and then it has some success criteria that are in statistical terms, meeting hypothesis tests. So I have 2 high-level stat issues that I wanted to talk about. The first one is the issue that what we call non-disparate bias, this is what statistically we would call an equivalence test. The goal is to show that whatever difference in bias there is between dark and light-skinned individuals, it's small. Too much bias either way is not acceptable. And we call this in statistics an equivalence test. And the way to do that is to test for equivalence. The easiest way to do that is to do what we call a 2 one-sided test approach. We test the upper limit, we test against the lower limit, both at the same alpha level, 0.05. What we don't do is split the alpha in half. And so the implication of that is the recommendation that FDA has to use a 2.5 and a 97.5 ends of a 95% interval is inappropriately conservative. The correct CI-based approach is to calculate a 90% confidence interval and show that that confidence interval is within the equivalence bounds. And so any sample size calculations that we're going to do should reflect this notion that what we're trying to do is test for equivalence and use the appropriate levels. And practically speaking, what that means is the sample size that you would calculate should be reduced. If you use the correct 2 one-sided test approach, is a fair amount smaller than when you don't do that. So there is a practical implication here. Okay, and the other high-level issue is that this draft guidance actually requires that you meet 9 different co-primary endpoints. And I made a little chart to sort of chart out what we're doing here. First, we have the test for ARMS that was previously used. And then for the low SaO2 ranges, we have these tests between the 3 different MST groups, high, medium, and low. So there's 3 different hypotheses we're testing here on this side. And in the high SaO2 range, we're doing the same thing. We're testing between these 3 different MST groups, all for equivalence. That's 3 more hypothesis tests we need to do. And then for ITA, we have to test the slope in the low SaO2 range, and we have to test the slope in the high SaO2 range. So that's 2, 6, 1. That's 9 separate hypotheses that you need to meet. in order to succeed the way that it's written now. Okay, and the problem with that is if you require that 9 hypotheses are met simultaneously in order to succeed, that decreases the power immensely. And this is a well-recognized problem when you have multiple co-primary endpoints. And the reason the power is decreased is because when we design a study, we design it so a good device has a high probability to succeed. That's what we call the power. And most studies have a target power of 80 or 90% for one outcome. So if you have a good device and you have a good sample size, then your probability of succeeding is 80 or 90%. It's quite high. But if you have multiple outcomes that you need to meet all of them, then your overall chance of meeting all of those goes down significantly. And the way you calculate is basically by multiplying out the power. So if you have 0.9, 0.9, 0.8, 0.8, and you multiply them all together, you get 0.5. That's a serious reduction in overall power. So this plot shows exactly what happens when you have initial power. So each of the individual endpoints has 90, 95, 85, 80%. And as you do these multiple comparisons from 1, 2, 3, 4, all the way out to 9, the power goes down a lot. The reason it goes down is because you have to meet every single one of those. And the amount it goes down depends on whether the outcomes are correlated or not. And these 4 lines on this chart show sort of the range of realistic correlation between hypothesis tests. So the worrisome thing is, so if you want to have high overall power for your study to meet all 9 of these endpoints, you have to build in the power loss due to this multiple comparison issue. So if you want 85% overall power, what you really need to do is target each of the individual comparisons to somewhere around 95%. So much larger sample size because you have so many co-primary endpoints. And this chart shows what happens if your goal is to meet 85% here, you want to have 85% at 9, as you test 9 hypotheses, you got to project backwards. How much power do I need to design each of the individual endpoints for to get to meet that target after 9? And the answer is somewhere in the 90+% range. So if you insist on having 9 multiple co-primary endpoints, then you need to design the study with a lot more power for each of the individuals to meet that. So just to be clear, this isn't Gary just ranting, because other parts of FDA have also recognized this issue. And a couple of years ago, the other parts of FDA, CDER and CBER, put out a guidance on multiple endpoints in clinical trials. They talk about the issue about the increased type 2 error. That means decreased study power. And they basically recommend that unless it's super important, using more than 2 co-primary endpoints is not a good idea. One more point, if you are insisting that we still need to use multiple co-primary endpoints, there's better ways to test it than one at a time. One recommendation is to group them into sets that make sense and test those groups all at once. So for example, we could take, instead of requiring each MST and ITA co-primary endpoint being tested individually, we could group them together. So for example, do all 6 of them pairwise MST comparisons with one statistical test. So that would mitigate the power. You would gain some of it back, not all, but some. So after all that, the high-level recommendations to FDA is, number 1, leave the RMS test as is. Number 2, from my point of view, the MST non-disparate bias with the 6 separate tests is not really required for a formal test. That maybe we could require reporting the outcomes by those categories given the confidence intervals, but not actually require that a separate statistical test be met for each of those. And then for the ITA slope, you could easily just combine that into one SDS across all SaO2 levels and test a single test for ITA slope. That would give you 2 endpoints, ARMS and a formal test for non-disparate bias. It would meet the requirement to formally show that the product didn't have too much non-disparate bias. It would allow you to report the MST subgroups so people could look at those and decide how they feel about the product. So that's it. Thanks a lot, Mike.
Thanks a lot. Appreciate that. And keep an eye on for the speakers and other statisticians on the call and other folks, please keep an eye on the chat. Next up is going to be David Bilks and Tim Hansen. If you guys want to start sharing your screen, we will hand the mic over to you. Gary, if you want to start, stop screen share on yours, if you don't mind.
Okay, yeah.
And David and Tim, if you want to just do a brief intro.
Yep. I'm David Milks, principal statistician at Medtronic.
Yeah. Hi, I'm Tim Hansen, senior program manager in corporate at Medtronic, program director.
Okay, so Medtronic is also a member of ISO JW G10 working group. So we've been looking at all of the different models for differential bias, and then sample size methodologies and study design. So just a summary of the approaches we started looking at. I think they've all been pretty well summarized, so far. We started looking at what we call the FDA, which is something we helped develop initial code for, just a linear mixed model. OpenOx is what we've heard from Danny and Tyler. What is specified in ISO right now, which is a regression of the sample subject-specific bias and ITA, and that ISO model with an additional random effects. Looking at things like this, because ISO is also having these models there, standardizing an approach. So we're looking at also what is the best model that we could possibly have standardized within the ISO standard. So ISO and the ISO plus the random effect averages across SpO2 minus SaO2 bias over the full SaO2 range in each of the 270 to 85, 85 to 100 saturations using sample means. The random effects was added to the simple linear regression model within ISO to account for repeated measures within subjects. The results didn't really change much due to the large number of repeated measures across the sampled number of subjects in a study design. So ISO and the random effects non-parametric addition using the sample means over those saturation ranges, FDA and ISO are parametric. So the average fitted across the regression line, which can also affect inference and needed to be checked. We'll go into more of these models right after this. And we focused on the OpenOx symmetry model developed by UCSF as they modified the initial linear mixed model from the FDA suggested. Again, not suggested by the FDA guidance, just something that we all worked on early on within the joint working group as being closer to the simple linear regression model and more easily interpretable. Tim?
Yeah, can you hear me okay?
Yep.
Okay, there's the models that we looked at with the Greek letters and everything. And the point is we have ISO, the simple regression, but then we added a random effect. It's something that we talked about in an ISO meeting a week or two ago. Does that make a difference? I was curious. It's something that the FDA and OpenOx symmetry have, although they have repeated measures. They have basically a separate slope for each subject. So we just added that in to account for the repeated measures, and sometimes subjects don't have the same numbers. And in the simple ISO model, I was a little bit worried that maybe the weighting wouldn't be quite right. And so we wanted to double check that. And then the OpenOx symmetry model on the bottom has a separate subject-specific line, intercept and slope, so that subject-specific line for each subject. There's a few more assumptions there. And I do have one plot coming up where we check it and it does make sense. And most of the sensors we looked at, that linearity in both ITA and saturation was pretty good, but in some it wasn't. In some there was some curvature. And yeah, just leave it there. I will say that in terms of the punchline is in terms of the sample size, you'll see shortly that you can do really well with a well-performing device in 20 to 30, sometimes 40, 50 subjects, but it is very important to get a representative ITA sample across the values that are in the population. So those are the models that we looked at. You want to go ahead to the next slide, David. And we, instead of what Danny did, we did look at simulation as well. We just did the clustered bootstrap. And something we thought about, I believe it's in the FDA guidance, I think Scott pointed that out, is that you actually want to make sure that you have something like a stratified clustered bootstrap to make sure you have representative numbers of ITA values in the ranges. So that was something we added to the clustered bootstrap, and it actually increased the power a little bit. In some cases, a fair amount. And the clustered bootstrap, we've seen it before in ISO meetings. It just uses the variability in the sample to estimate the variability in the population. They're a little bit hamstrung. You can't really tweak anything. You basically have to have pilot data and assume that your population is going to continue to follow the pilot data. One of the things we will be looking at is doing more what Danny did and just the simulate, and other people, is the simulation, so we can tweak some things in terms of the ITA distribution. ISO doesn't really have, we use cutoffs 1 and 1.5 and 3.5 per FDA instead of 2 and 4. And then we modified to use the 2 one-sided sample thing that Gary was talking about. And the one thing we did is, since we do like looking at the 2 ranges separately, we did use 95% confidence intervals so that we're testing each range at 2.5%, and then through Bonferroni, the total is 5%. And as Gary mentioned, you can modify that. That's probably the most conservative approach to go, but you could use something. These test statistics are going to be correlated, so there might be ways to improve the power using that as well. So these are the approaches. The second to the last bullet point is probably pretty important. The power was similar among simple ISO using these cutoffs, adding random effects to the ISO, and OpenOx symmetry. There were some differences, and we have some power curves for a handful of devices to show you. So you can keep going, David.
Okay. Before we get into those power curves here, we'll just give some quick conclusions, of what we saw. Really looking as well ahead now, I think, a lot of us are aligned. There's variability in devices, in performance, and a sample size required. So the one thing we really wanted to highlight was a sample size for the hypoxia clinical verification of accuracy should be based on a well-designed study. And I believe that's always been a part of the ISO standard, that you shall statistically justify your number of subjects and your study design. I think we can agree that a minimum of 24, again, that is what is being proposed as standardized within ISO 80601-2-61, makes sense. And looking at the power at 80% across a lot of this open oximetry data, at n equals 24, the systems are meeting the requirements of disparate bias, differential bias, with the confidence limits at 1.5 and 3.5% thresholds at both the low and the high saturation ranges. One thing that we're still investigating is this promising zone approach to an adaptive design, which could be easy to implement, bounding type 1 error incurred from multiple tests. Again, something we're investigating now on how we would develop, the verification study going forward, starting with an initial sample size, maybe based on pilot data, predicate system hypoxia data, and then that first look at that minimum sample size and testing the hypothesis to the acceptance criterions by the FDA. And then that sample size re-estimation, if that sample size was sufficient with statistical power, or what number of subjects would be needed after. So really looking at the study design on how we would move forward from anything standardized within ISO, and then how you would have a defendable sample size and study output to present to the FDA. The ISO linear regression method for differential bias is preferred at this point, in the investigation of statistical models. And that was going through looking at all the approaches, the pros and cons. Tim went into some of that, and understanding that balance of complexity of statistics and benefit, between the models. So I'll let Tim now quickly get into a couple of the slides here. Again, this is from the open oximetry data provided to us.
Thanks, David. So here's an example of the sample size. This is just our code, but for this particular device, which performs pretty darn well, device 11, you have the sample sizes in the low sat range to get 80% power. So 25, 26, 26, they're all similar. And the upper range, 30, 33, 20. And it's for this particular device, I would say that the sample size of 150 probably isn't needed. There's the law of diminishing returns as you go up, depending on how much power that you want. And this is typical of what we saw, but there were some cases where the power could be quite different across the approaches. And this is part of our argument for using simple ISO for this. Next slide. Yeah, we don't need this. We've seen plots like this before. This is the open oximetry and the FDA model that we've looked at. It has linearity and saturation. So this just shows you the subject-specific intercepts and slopes and how they change with ITA. And this is representative. They change linearly. Usually that model is great. For one of our sensors, it didn't fit very well. But here it looks great. You want those to be linear, and they are, arguably. Now let's look at another sensor. This is an example of a device that was close to the threshold, and at least we just went up to 100 with the clustered bootstrap. It's just not going to happen. If you're too close, there's, in some sense, there's no sample size that's going to get you to where you want. I think we have one more. And here's another one that's a little bit split. So in the low sat range, we're doing quite well. And in the higher range, we can get there eventually. But it looks like it's going to be sample size of over 100 to get there.
Thanks, right. Tim.
Yep.
Yeah, I think that's it, Mike. Hey, Bob, thank you for the reminder. So Medtronic is the manufacturer of the Nellcore pulse oximeters. I might not have mentioned when I introduced us.
Thanks, David. We're going to transition over to the last speaker, and then we'll have some discussion while Evan is pulling up his slides. I can also mention that there's a lot of collaborators in the OpenOx collaborative community, industry, academics, regulatory. A lot of us work together to try and think in these forums. And we hope that can continue and everybody can share their disclosures. For those who don't know, the Hypoxia Lab, we do testing for a number of devices and work with manufacturers on the testing of their devices from time to time. All the data that you're seeing presented by our team today was collected independently without input or involvement of manufacturers in the selection of devices, the collection of data, or the analysis. We've just been sharing our data sets openly with anybody who's interested in seeing them. Evan, if you have slides that you want to share, you can go ahead and share your slides.
Sounds good. All right, we're just going to leave PowerPoint in as it is, but thank you, Michael. Hello, everybody. My name is Evan Amadown. I'm from Element Boulder. We're one of the testing facilities for hypoxia studies. Before I begin, got to shout out the rest of my colleagues, Rachel, Tanya, and Keen, for their work on this. It's truly a team effort, and I just get lucky enough to present to you all today. So what we did with our data is created a data set of approximately 185 participants with approximately 1/3 in each of the Monk and ITA cohorts and about a 50-50 split between male and female. The data set had paired SpO2 and SaO2 data from 3 control oximeters that we utilize within the lab with varying performances. Do note the convention of performance is all relative to each other and not an absolute designation of performance of the oximeter. So what we did was took sample sizes of 12 up to 150 in increments of 12 and did 10,000 clustered bootstraps on each, and then maintained that 1/3 split between each cohort. From each of those, we calculated ARMS and ITA-based non-disparate bias in each of the SaO2 ranges, and then similar to what the folks at Medtronic did, calculated power for each of these to see really what sample size best balances statistical power with, practical implementation of testing. So on the ARMS side, you can see that a moderately performing oximeter has about a 90% power with 12 participants. And then what we designated as more poorly performing, quote unquote, hits that 80% mark. That's been talked about right at about 48 participants. We also calculated the confidence intervals around each ARMS calculated per sample size. I know there's a lot of lines going on. Really, the important one to look at here is the green line. So the solid one represents the ARMS of each sample size, while the dashed ones of the same color represent its 95% confidence interval. So here in this case, you can see on the poorly performing oximeter up to or starting at a sample size of 48, there is no chance of that poorly performing oximeter accidentally passing with a ARMS due to the confidence intervals being above that 3.0 threshold right at about 48 participants. So similar to what's been previously said, there's diminishing returns after that as far as being confident in your calculated values at that point. Similarly, we also looked at the non-disparate bias utilizing the ISO simple linear model as well. Similar story here, that range of 24 to 48-ish participants for both moderately and poorly performing devices achieve the noted 80% power that's needed. And on a well-performing device, you're above that and confident well before that kind of larger sample size then. Same thing, or at least similar story as far as looking at the non-disparate bias, the point estimates plus the confidence intervals for each of the saturation ranges. So looking at the figure on the left, utilizing the FDA threshold of 3.5, you can see that both the moderate and poorly performing oximeter achieve a passing, quote unquote, results at around a sample size of 36 to 48 participants at that point. The more interesting find is that in the upper saturation range, the FDA criteria of 1.5% or less isn't achieved until around more the 100 to 120 participant kind of range for these oximeters, which is really quite different than what is required for the lower range and to properly power your ARMS as well. So concluding from those, really a sample size of 24 to 48 is optimal. It properly balances our statistical power and statistical gain per participant, right? As was previously mentioned, the law of diminishing returns. In that range, we adequately power our study and will properly fail bad oximeters while correctly passing good oximeters. And then to summarize a little bit more on the last slide, that FDA criteria of 1.5% in the upper saturation range is likely too stringent just because it required a sample size roughly 5 times that of what's suggested by the other statistics on the same oximeters, and that the ISO recommended criteria of 2% in this range is likely more reasonable and suggests a similar number of participants to the other statistics as well. So sorry to be quick through that, just trying to keep everybody and everything on time.
Thanks a lot, Evan. That was great. We have about 5 minutes left. If folks can be putting stuff into the chat or questions, or feel free to raise your hand. Francois Lelouch, I see a comment. This is a great point and worth mentioning. All the data that you're seeing have been collected in controlled desaturation studies in healthy volunteers in laboratories that test pulse oximeter performance. These are healthy volunteers. That means that they tend to be relatively young. They do not have comorbidities that you'd see in patients in the real world. They have normal blood pressure and a variety of other factors that just aren't present in real world patient studies. So the performance in the lab and the performance in real world patients is not the same. And so the guidance and standard are referring to performance, generally speaking, of these devices under these somewhat idealized conditions. So thanks for pointing that out, Francois. I think that's a very relevant and important point here. Other questions? Anyone, feel free to raise your hand or put them in the chat. Howard, is sampling of patients relevant? Howard, can you clarify? Do you want to take yourself off mute and clarify the question?
Yeah, I guess more so like, are we getting kind of a sample, at least of the population of healthy subjects versus like in the lab, are you seeing specific outliers that don't make sense?
That's a great question. So two quick responses, and other speakers feel free to chime in. So for the first time, to my knowledge, in the new draft FDA guidance, there is a new stipulation that requires reporting of consecutive subjects. So if we enroll, 300 subjects, let's say, and we need to produce a data set of 150 of them for FDA clearance, we need to choose 150 consecutive subjects. Or sometimes there are subjects that drop out and are not able to complete the study because of intolerance of hypoxemia, for example, something like that. Those would be excluded. But otherwise, we can't cherry pick from the 300. We have to pick consecutive subjects. That's a good positive improvement. That means that there is less likely to be sampling error where you are avoiding these outliers. But yes, there are sometimes outliers in performance. Now those will be included, and it is a major focus of our lab and likely others to try and better understand for these outliers why they are indeed outliers. Bob, I see your hand. Over to you.
Just a quick question for Tyler's presentation. He showed a subject number, I think it was 32, and then there was another, but I couldn't catch the number quickly from my screen size. Is there anything that you are seeing? I mean, this may be an outlier, but is there anything that you might have been aware of in retrospect, looking at the documentation in the notes for sensor positioning, for motion, for PI, any other issue that would show why that occult hypoxia was so pronounced? And it was inconsistent, meaning there wasn't great linearity in performance. Tyler?
Thanks, Bob. It's always interesting to look at the people who perform differently and try and figure out why. For some of those things, we try as best we can to rule out some of those common factors like propositioning, artifact, etc. And so we're trying, obviously, not to accept points that are suspect in that regard. I think a lot of the time, I can't remember exactly. I'm looking through, but I can't remember exactly which points you were talking about. But a lot of the time, what you observe are the people who are consistently off in one direction throughout the saturation range. So we're highlighting the occult bias because that's the range that we've brought attention to. But it's throughout the sat range that we see a lot of time that person. Remember, I showed that a figure of people having their own regression line there that's kind of separate, and that seems to be quite frequent. But yeah, a detailed analysis into the outliers throughout these is a great step as well.
Eric, I see a question from you. Do you want to take yourself off mute and comment?
Hi, Mike. Hi, everybody. It's more just of a general comment, and this is something that our group, including Shubhata, we've talked about extensively, is just around how these guidances, will potentially impact children and who already have a lack of access to devices, especially in resource-constrained settings, and just the need for, application of these accuracy studies in the real world to children, rather than just assume that devices tested and designed on adults will just work the same on children, which is, we're seeing data supporting that that's not the case.
Thanks, Eric. Appreciate that. For those of you who haven't seen, there's a paper in New England Journal this week on a study in pediatric patients. Relatively little data there, so worth checking out. Of note, that study did use fractional saturation instead of functional saturation, so there are some major caveats in terms of the magnitude of error that they did show. But a very important point on kids. There are some new changes in the new draft guidance that do require a little bit more data, including, to Francois's point, a little bit more data from pediatric populations, whereas only neonatal populations were required to have some convenient sampling to demonstrate performance. So that does appear to be a positive step forward. it's probably well beyond the scope of this discussion because we're right at time, but this is an important topic that's kind of playing out in the chat right now of if the lab studies don't necessarily equate to real world clinical performance, why not just do more clinical trials? And I think the answer to that question will become more apparent as we see more large prospective clinical trials published that are going to demonstrate there are many more questions than there are answers. I will leave that there. And Shubhita, I see your hand. We'll go to you for the final question here, and then we'll wrap.
Thanks, Mike. Just an idea that came up when you all are doing your measurements in the lab setting, are you measuring the digit surface temperatures? Just kind of anecdotally, pulse oximeters don't work very well in me, and it's because my fingers are constantly very cold. I was just curious if that was being collected.
Yeah, thanks, Shubhita. We have in cohorts measured surface temperature. Our hypothesis around that is that is correlating with other factors like pulsatility, amplitude, perfusion, et cetera. And so we're trying to use more direct measures for that. And so have some special protocols to try and quantify that. But we have not released any of that data. And happy to chat more about that offline. But yeah, good point. All right, well, we are up on the hour. We appreciate everybody's time. Thank you very much to all the speakers who put in time to create these presentations. This is going to be an ongoing discussion. As mentioned at the beginning, the draft FDA guidance is open for public comment, so would encourage any groups who are, have data, are analyzing data to make comment so that we can try and ensure that these the new guidance is as impactful as possible for kids, for people of various skin colors, and for people around the world. So thank you very much. And we will be posting this video in the next 24 hours to the OpenOx Symmetry website, along with some of the content. Thanks very much. Appreciate it.